Okay. Yes, I thought when I was invited to give the talk that I hedged my bets with the title. I thought aerospace, because I don't know much about space technology, to be honest. I'm a graphene person. But then I thought, well, I'll have a look and see what's going on. And it turned out that, quite a lot. And so I thought, well, why not go the whole hog and consider space technology, rather than just aerospace. So we'll leave the airplanes out of it, and we'll just think about space, rockets, and getting things up in space, and how graphene might help. And I have to say, I didn't realize I was talking to such a group of dedicated people. I mean, crikey, going out at 3:30 in the morning onto the hillside to see a dot in the sky. Gosh. Yes, you. I envy you. Yeah, okay, so first of all, I'm going to say a little bit about what graphene is. Not everybody has a picture of what graphene is, and there's certainly some confusing nomenclature when it comes to graphene. I'm going to use some little models on this table. I'll hold them up for people so they can see them on camera. First of all, graphene itself is often called a 2D material. And people have often asked me, well, what do you mean by two-dimensional? Because surely everything in our world is three-dimensional. And so when we think about two-dimensional materials, as scientists, and particular material scientists, would think, well, it's to do with the crystal structure and the way the material is formed. So graphene comes from graphite. Graphite is essentially a multi-layer structure. So it consists of these layers of carbon atoms held together by some very strong bonds. And they're in a plane, and these bonds are incredibly strong. It's very difficult to break these bonds. They're the strongest bonds in nature, which means graphene itself is a very strong material. So graphite is just a stack of these things, stacked in a particular way. But the bonds between these layers are incredibly weak. So these layers slide over one another very easily. Graphite is often used as a lubricant because of that. And if we think about graphite itself, well, graphite's in pencils. And if you take a pencil across a piece of paper, you leave a mark. And the mark you leave behind are these layers that have peeled off, essentially. So that's essentially why it should be relatively straightforward, you would think, to actually produce graphene. But as you'll see later, it actually isn't that easy. In fact, the materials that preceded graphene were things like nanotubes. Now, a nanotube is just that sheet of carbon atoms rolled into a tube. And we often call these one-dimensional materials. And then there's a thing called a buckyball, which again is obtained from that sheet by cutting out a particular shape and bending it round to produce a completely closed structure. So this completely closed structure is often called a zero-dimensional material. So why is that? Well, if we think about graphite as a three-dimensional material, if I want to make more graphite, if I want to grow more graphite, I can either add layers, or I can grow it this way, grow each layer that way, or I can grow each layer that way. So I have 1, 2, 3 dimensions in which I can actually grow that structure, make a bigger piece. If I think about this material, though, if I don't break it up and I want to add more atoms, the only places I've got to add them are here and here. So I can grow it that way, but in one dimension. If I want to add more atoms to this structure, though, not without breaking it up, okay? So we call that zero dimensional because I can't make it any bigger without breaking it apart, essentially. So hopefully that gives a little bit of an explanation as to why we call graphene a two-dimensional material. So this wheel's tricky to sorry, I'm dashing backwards and forwards, but it's really quite tricky to control. Now, in 1947, a guy called Philip Wallace was the first person to study graphene. And the reason he was interested in graphene is because it comes from graphite. He wanted to model graphite. Anybody have any idea why he might have wanted to model graphite in 1940s? Yeah, reactors, that's right. Nuclear reactors used graphite as a moderator, and so people want to know a lot about the properties of graphite. Theoretical material scientists, oh, okay, he wanted to model it. Of course, they didn't have computers in those days that were capable of modeling these sorts of things, three-dimensional structures of this sort of complexity. So Wallace hit upon the idea of just considering a single layer. And it turned out that he could actually analyze that analytically without having to go to the sort of models we use today, which are really models based on our ability to do fairly complex computations in computers. And so he thought, well, if I study this material, it'll give me some idea of what's going on in graphite. And he discovered that this theoretical single layer had lots of interesting properties. So he'd already uncovered some of the properties of graphene. In fact, when Andre Geim first isolated it, started studying it, it was the paper written by Wallace that he used to decide what properties to actually investigate first. And one of the properties was an electrical property that this guy had proposed. So then in 68, move on to 68, where some other theoreticians, Mermin, Landau, and Peels, they were interested in looking at theoretically what a two-dimensional crystal would be, how it would exist. And they decided that it would actually not exist. It would be thermodynamically unstable because there are no atoms above or below that plane to stop these atoms vibrating away. And of course, anything that's at normal temperatures will be vibrating. It's got energy, it will vibrate. There's nothing to stop them vibrating out of that plane quite a long way. And so they decided that this thing would just fall apart. It would just crumble into a lump of, in this case, it was carbon soot, okay? So it would form a particle, a big particle, rather than stay as a nice two-dimensional single crystal. So they thought, okay, it's not stable. The term graphene itself was first mentioned by Morose and co-workers in 1987. They just needed a name because they were looking again at graphite, and they wanted a name for this individual layer. So again, a theoretical idea that it was an individual layer, it's a theoretical abstraction, wasn't real, couldn't exist, because these other guys had said thermodynamically it's unstable. So it can't exist in nature on its own, but it can exist as a stack in graphite. So move on now to 2004, when these guys, Andre Geim and Kostyan and Vossilov, actually isolated a single layer of this material. And it was incredibly difficult to get the first paper published because people said, no, it can't exist. Look, it's a theory, it says it can't exist. And so they had to go to great lengths to prove that it was actually single layer. It did exist in its own right. It could exist on a surface, or it could exist unsuspended in space, as it were. And so it took a long time to convince the editors of the relevant journals that actually it was worth publishing. go forward a few years, and of course they get the Nobel Prize in Physics for studying the properties of it. So in fact, it was a groundbreaking achievement. Interestingly, Andre Geim is one of the few people I know who has the Nobel Prize and the Ig Nobel Prize. The Ig Nobel Prize is a kind of jokey prize for people who've done experiments which are somewhat weird. His weird experiment was floating a frog in a magnetic field. Okay. And I remember we used to joke about this over coffee, and he said, well, the reason he floated the frog was when he was working in Nijmegen on this big magnetic facility, he wanted to show that water in a magnetic field would actually be suspended. And so he wanted to pour water into their, really, really expensive magnet. And they said, no, you're not doing that. So first of all, he put tomatoes in. And then he went to the idea, well, why not a frog? It's just a bag of water. So essentially, anybody who has drawn with a pencil will have actually produced graphene. So if you've drawn with a pencil, you'll have produced some graphene. It's that easy to make. But it's very difficult to find it. It's very difficult to show that you actually made some graphene. So that's the trick. And when we started with this work, we started with lumps of graphite, and Andre wanted to know how thin you could make it. And so he and I had a joint student who was polishing it down to try and make really thin layers of this stuff. And then one day, Andre was talking to a materials scientist who said, oh, graphite, yeah, we use that. We use that to calibrate all our equipment. Because it's really easy to get a nice clean surface. So we're surface scientists, and we need clean surfaces to calibrate all our setups. So what we do is we put some sticky tape on the surface, peel it off, and it leaves a beautiful clean surface behind. And he said, I bet that material that's left on that sticky tape is thinner than the stuff that your guy is producing with his polishing. So Andre sent Kostya, who was his student at the time, his research assistant at the time, off to investigate this and see if it was true. And Kostya got some tape and decided to split the stuff up and try and make a single layer of graphene. Now, Kostya is probably the best experimental physicist I've ever come across. He can make anything work. And so what he did was he took some sellotape and he essentially put it onto a lump of graphite and then peeled it away. And then he put it onto, he put the sticky tape onto some silicon and pulled it off and left some material behind. Just to show you how easy that is, I've actually got a little demonstration here of how we do it. So first of all, this is just a piece of sticky tape, and that little dot that you can see on the sticky tape, or some of you can see, is actually just a bit of graphite. So I put this bit of graphite on there, and what I'm going to attempt to do, assuming this hasn't welded itself together, so I can't separate it, which it sometimes does. Yep, right, come it apart. I'm going to pull it apart like that, and lo and behold, I now have two dots. It just peeled it. So it's peeled those layers apart. And if I keep doing that, I can show you the result of that. That's one where we've peeled the two dots, okay? So you can see two dots on that one. If I keep putting this together, but pulling it apart like that, you can see I don't put it back in exactly the same pace. I slightly move it to one side. And what I end up with is a little cloud of dots like that. Look at that, okay? And somewhere in that cloud will actually be some graphene. The problem with it is finding where it is, because there's a whole lot of rubbish there. Okay, but Kostya, being Kostya, managed to actually show that what you could actually do by putting it onto silicon, in fact, it's actually on silicon dioxide, because the silicon is covered with a thin oxide layer. Most silicon is. And if we put it onto that surface, then you'll find some flakes that look like that. And you can see there, I've indicated a kind of a monolayer. Oops, go back. I've indicated a kind of monolayer, which is by eye now. This is what we got used to looking at. When we've done all the measurements, we found that particular level of contrast was a single layer. We never saw anything lighter than that, only darker. And so that's a single layer. You can see there's a bilayer there as well. Note the contrast, very high contrast. I'll come back to that in a minute. So if we looked at that tape you're looking at now under a microscope, this is what we would see. Okay, and you can see that some areas are just chunks of graphite, and other areas are much, much thinner. And you can see some very thin, transparent areas. Here I've tried to indicate the sort of how dark something would be. So you can see if I look at single layer, you wouldn't see it, because it's almost the same as the background. It's identical to the background virtually. So you won't see single layer this way. That's why you have to put it on silicon dioxide, in order to see it. But some of the other layers, like 9, 10, you can definitely see, because some of these are sort of 9, 10 layers thick. So you can actually make what we would call graphenes, but they're multi-layer graphenes. They're not yet graphite, because you have to get to about 20 layers or so before you start seeing the properties of graphite in the material. So these do have different properties from graphite. Unfortunately, the multi-layer ones also have different properties from graphene. So it's a complex business looking at these things. Let's see if I can move on. Yeah. It's not letting me move on. Why is that? What's happened? Oh. Ah, right, okay.
Told you, when it goes laser pointer, it doesn't always.
Yeah. So back to this silicon and the importance of it. Kostya came over to the clean rooms and said, you know, have you got any silicon wafers? And I said yes, and gave him some silicon wafers, and he went away with them. And he started putting this stuff on the silicon wafers, and he could see these materials. And it just so happened that the sort of material we had was happened to have 300 nanometers of oxide on the surface. So quite a very thin layer of oxide on the surface. But it turned out that was just about the right thickness to see the layers. Because if you look at different layers, for example, if you look at 410 nanometers up there, you can't see any graphene at all. And we discovered that when a new batch of wafers arrived with a different thickness of oxide, because we weren't bothered about how thick it was, as long as there was oxide there for some of our experiments, that's all we needed. And Kostya said, "Oh, I'm not making graphene anymore. Something's wrong." So he went away and he dug into various issues, what kind of tape he was using, etc., etc., and eventually what type of graphite, and eventually. It was a student of mine that developed a model that showed that the thickness of that oxide is quite critical in seeing the graphene. Also, the color of the light that you're using is quite critical as well. So it was in a way somewhat fortuitous that he was ever able to see it in the first place. So if we'd had 410 nanometer oxide graphene, he wouldn't have seen it. And we may not be where we are today. And of course, it's so easy to make. This peeling technique is so easy. We've taken this on various exhibitions for kids to make some graphene and have a look through a microscope at what they've made. But that's all very well for making it in a lab for laboratory experiments, but can you make it on large scale? And if you're ever going to use it for applications, space and so on, space technology, you're going to need large quantities of it. Well, there are two types of graphene that we commonly use. One is sheet material, which is just a single sheet of material like that. And the other is powder, which is just little flakes of the single sheet material. And the question is, how do you make those different types? Well, the graphene sheets are made by a process called chemical vapor deposition, CVD. And what they do is they take some copper foil. Copper is important because it acts as a catalyst in the process. You put it into a furnace at about 1100, 1200 degrees, and you pass a source of carbon over it. The source of carbon usually used is methane. So you pass some methane gas over it, and lo and behold, where you've got exposed copper, the methane breaks up and the carbon deposits on the surface as graphene. And when you've got the graphene deposited on the surface, the gas can't see the copper anymore, and so the process stops. So it's a self-limiting process for producing nice thin layers of graphene sheet material. And then if you want to do experiments on it, often we want to do experiments, electrical experiments, things like that. Well, it's on copper, which is a good conductor, so you don't really want it on copper. You want to put it on some other material. Well, you can actually remove it from the copper. There are various processes now. There's even a roll-to-roll process for doing it. Samsung sunk a lot of money into doing that because what they were interested in was flexible touch screens. Graphene is transparent and conductive. So this is exactly the material you need to put on a touch screen in order to put the electrodes in to work out where your finger is. And so essentially that's why Samsung were really interested in it. In fact, we wonder whether graphene is involved in their new flip phone with a folding screen. We don't know because they won't release any details on it, so we can't tell. But we think it might be because they did put a lot of money into it. What about powder? Well, powder is relatively easy to produce. What you do is you put some graphite into a bath, a chemical bath, very strong oxidizer, sulfuric acid and potassium permanganate, really, really strong oxidizer. And what it does is it pops chemical groups, OH groups in this case, between the layers. And to do that, the layers are forced apart. And because the layers are forced apart, okay, then they're bonded less strongly together. And then what you can then do, having forced them apart, is you can reduce that oxide back to the graphene by removing the OH groups, using hydrogen or some other technique. And then you can ultrasonicate that to split these layers completely apart, because they're now quite weak and they just fall apart quite easily. And you can produce stable graphene dispersions and things like that. So you can produce this kind of liquid with graphene suspended in it. And if you use a centrifuge, you can actually separate out the light layers from the heavy layers. So you can make sure that you've only got, say, single layer graphene, the very lightest layers, and then you get 2-layer, 3-layer, 4-layer, so on. So it is possible to separate these things out. Now, I just mentioned a property of graphene oxide, this material that you make by oxidizing graphene, because it's quite an interesting property, and it does play a part later on. Graphene oxide can be made into laminates. You can actually press this powder together and form these sort of laminated structures. And they have little nano channels between the layers. And these channels are quite interesting because if you take some of this graphene oxide, it won't let helium through at all. Helium's a very light atom. It should zip through it, but it doesn't. It won't go through. But if you replace that helium with water vapor, that goes through very, very easily. And the reason for that is that the channels are actually filled with water, essentially. So they have molecular water, which is bonded in there and stops anything else going through except water, because the water can replace the water molecules through the channel. So although it looks like a bit of an oxymoron there, it isn't. It works quite nicely, that. And of course, further work has been done to make filters out of this stuff. And one of the things that we found is that you can actually, you can filter out molecules of different sizes because you can make that cutoff between where the molecules will go through and where they won't. You can make that programmable, so you can change it, you can move it up and down. So obviously, as a filter material, this looks quite interesting. I just mentioned that, we'll see that later on. Now, there is another way of making that powder. This is an electrochemical technique. We put some graphite into a beaker full of electrolyte, make a circuit, so we're driving some electric current around there, and what do we find? We find that the electrolyte ions get in between the layers and force the layers apart. And you can see that happening there. Of course, it would be nice if that were just the top layer that was peeling off, but of course we can't control where that is. It could be anywhere in that structure. So there will be some heavy lumps of graphite that come off, as well as some multi-layer graphenes and some single-layer graphene. You can see the heavier stuff falling there under gravity. And of course, what we can do is if we centrifuge it, okay, then we can increase that effect. And so we can take off all the light stuff, all of the nice powder, as it were. So let's have a look at the properties of graphene now and see how they might be exploited in space technology. Well, one of the most important properties, and I can't emphasize this enough as an academic, is it's very good at attracting research. And you can see how this played out, because remember this guy, George Osborne, the Chancellor there, he got very interested in graphene. He was straight onto the bandwagon, and he decided that he would give Manchester some money to produce a building in which we would study it. And this was useful for us because we were overcrowded in the centre I was running. We were absolutely jam-packed. Virtually all the work that was going on there by this time was graphene work, and so we needed somewhere to expand into. And so we reckon that George was interested because graphene is so stretchable and thin, all future government policies would be made of it. But I pointed out that it's also very transparent, so maybe not. It was Laurie Taylor who first pointed that out. So this was the building that was built with the money. The clean rooms are in the basement of this building. I helped design those and specified them, and then helped in their construction. So basically, what we did, we took all the experience we had from the other clean rooms from our Centre for Mesoscience and Nanotechnology and ploughed it into that building, and we ended up with quite a useful facility for studying the science. But then it was thought, well, maybe what about the engineering aspects of this material? Shouldn't somebody be working on that as well? So now we've got another centre, which is the Graphene Engineering and Innovation Centre, or GEEK, as it's called. And that is where all of the sort of, if you like, industry-facing stuff is done. Okay, all the applications, stuff like that. So let's have a look at the list. I've got a laundry list of properties for graphene here. It has the highest tensile strength of any material, 100 times that of steel. It's the thinnest two-dimensional material in the universe. It's almost entirely transparent. It's the best conductor of heat. As charge carriers, that's the things that carry electric current, which move with no effective mass. In other words, you can accelerate and decelerate these things very, very fast. So it's a fastest conductor of electricity we know. And it's one of the most elastic materials we know. It's one of the most flexible materials. Interestingly, though, it's immensely flexible when it's free, but if you clamp two edges, it becomes incredibly stiff. So if I clamp two edges of this material, it becomes immensely stiff. It took us a long time to work that one out because we found that we could suspend a flake of graphene in space for quite a long way, and yet when you had it on over a hole or something, you could bend it really easily. So we tried to work out why that was, and it turned out it depends on how you clamp the edges. If you let the edges be free, then it's flexible. You can bend it easily. But if you don't, if you clamp them down, then it becomes very stiff. And what we'd done is we'd put this flake out into space, and we'd coated the surrounding area with gold. So it was actually clamped around the edges. Of course, it's the lightest film we know. It's totally impermeable to even the smallest atom, helium. And the list would go on and on and on, chemically inert, blah, 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 blah. Okay. What I'm going to do here is just concentrate on three areas. It's very strong, okay? 100 times that of steel. Okay, it's the best conductor of heat that we've got, and it has charge carriers with no effective mass, so it conducts electricity very fast, so you can use it at very, very high frequencies if you want to make devices that work up in the terahertz range, for example. So thermal properties first. What do we mean by heat conductivity? Well, we know that if we heat one end of an object, how long does it take for heat to transfer itself down to the other end when we grab it? How hot would that end be? We know some materials are very insulating. We have a pan on the hob, and it's got a plastic handle. Then we know we can safely touch that. Got a metal handle. We sometimes have to make sure it's not too hot. It turns out that you really don't want a handle made of graphene because it is very, very good conductor and will burn your hand off without any trouble at all. So it's the best conductor of heat. It's better conductor than most metals, and it's a lot lighter than most metals. And one of its major applications is in removing heat from spacecraft and satellites, where you've got instrumentation which needs heat removing from it. Graphene is very, very useful for that. So this is a thermal strap made for a satellite for removing heat. And this one is a graphene-based one. Current ones that are currently in use are copper-based. This is made from bonded graphene. It has 10% of the mass of a copper one, and up to twice the thermal conductivity. So it's twice as efficient at getting rid of the heat, and it's a hell of a lot lighter. So getting it into space costs you a lot less. So obviously various companies, this is VTT mics, various companies are making this stuff now. A similar thing is a cooling loop. A cooling loop is just simply a means of moving heat from one part of a satellite or a spacecraft to another. You sometimes see heat pipes. I don't know if any of you ever looked inside a computer with a big heat sink on it, and sometimes you'll see these copper pipes on the heat sink, and those are actually heat pipes. And what you have in a heat pipe is a volatile material, and often it's alcohol, and that's inside a wick which runs through the length of the pipe, usually a copper sponge. And what happens at the hot end is that evaporates, travels down the heat pipe, condenses at the other end and deposits the heat. So it's a very efficient way of moving heat around the system. Turns out that if you make these heat pipes with graphene, you can make them about 3.5 times more efficient and a lot lighter. So a 90mm graphene heat pipe would weigh 2.1 grams, whereas its copper equivalent is 12.9 grams. So again, getting it into space, there's just no comparison. So a lot of work is being done. This particular one's made from a graphene polymer composite material as the pipe, and then carbon fiber is being used as the wick in this instance. It was found to be more efficient than a graphene version. So graphene is very strong. I've said that a few times now. How do we know it's very strong? Well, one of the ways is we took some of our little flakes and we put them over little holes that we'd etched into a suitable material, silicon nitride, and we took a little stylus, a little cantilever with a stylus on it, and we poked the surface like that, and we poked it hard enough so that it would rupture the surface. Now, these little cantilevers are on springs. So basically, essentially, as we poke into the surface, the spring deflects, and we can measure that deflection accurately to within a subatomic distance. So we can actually measure that very, very precisely. And that tells us what force we're putting on the surface, because we know the spring constant. And it turns out the experiment was really difficult to do, because our little cantilevers, the tip on the silicon kept breaking before it went through the surface. So we had to get stronger cantilever styluses in order to break through the surface. And then it turned out, when we looked at the results, that in fact it's got a tensile strength 200 times that of steel. So its tensile strength is huge. Also of importance is the fact that it's very light. So its strength to weight ratio is the highest of any known material. It's huge, absolutely huge. To give you some sort of example of that, if we scale the experiment up now from our little flake over the hole to a sheet which is equivalent to some cling film, thickness of some cling film. So we put some sheets together to make the thickness of cling film. What could that support? Well, if we put a pencil on there, we'd be able to stand an elephant or a large SUV on top of that pencil and it wouldn't go through. Whereas cling film, easy. So it is. Sorry? How many layers? 1,000, 2,000 maybe, something of that order. Maybe a bit more, because you've got to make up the thickness. Okay. Okay, I'm going to come on to some issues with this. This is not a practical experiment. Okay, this is just a theoretical notion to illustrate the point. Okay. To do this as a practical experiment, and we would like to do something similar to this as a practical experiment, it is going to be difficult. Because I don't know how many of you are familiar with space elevators. Yeah? The idea of space elevators has been around a long time. Solnikov came up with the idea, I think, of building a tower up to the sky, and then decided in the 60s that's not a practical proposition. It'd be much better to have a tether, a rope that goes up into the sky, into space, and at the end of that we put an anchor, just a massive object, be a space station, something. And because this thing is whirling around, it's connected to the Earth at the equator, so it's spinning around with the Earth. And you know, if you spin a rock around on a piece of string, it's going to try and pull away. So it tensions that piece of string. And so what we have here is we have two competing forces. We have the tension due to that anchor trying to move off into space and the weight of the rest of the boat trying to move off into space. And we have the effects of gravity on the lower part of that suspension, pulling it down to the ground. And at some point, those two forces must balance out. That's actually where we have a geostationary node. That's geostationary orbit. So we popped a satellite there, it will go around at the same rate as the Earth. And the idea is to build one of these things and to have a climber or crawler, which crawls up and down this tether and can take payloads into space, the people. When you look at some of the figures that are being quoted for this, I mean, first of all, the height to geostationary orbit is around about 36,000 kilometers, okay? So it's 35,786 kilometers or thereabouts. So from the surface of the Earth. So that's quite significant. But then the other end of the tether, they actually want to take it out far enough so that you could actually launch vehicles from that on interplanetary missions, and that takes it out to about 100 kilometers or thereabouts. So we're looking at a tether which is around about 100 kilometers, 100,000 kilometers long. So it's a huge ask to build something of that length. But more importantly, you think about it, it's got to be able to support its own weight. That's the first most important thing. And it turns out that if you tried to make that of steel, you could get to about 200 kilometers or thereabouts, and it would fall down, okay? It would break. So to get up to 100,000 kilometers, you need a material that's a lot stronger and much lighter. Graphene. In fact, it was proposed originally because these things came before graphene was isolated, okay, nanotubes, and people said, oh, these are very strong. We could make our rope of these, okay? But it's incredibly difficult to make those any length at all because, of course, you start growing them out and at some point there's going to be a fault or a bump or something that's going to weaken it, okay? And it's very difficult to grow them in the first place. So, so that turns out to be difficult. In fact, Elon Musk said, please don't talk about space elevators until someone can at least build a carbon nanotube structure longer than a footbridge. It turns out most components, apart from the tether, can be made with current or near-term technology. It's not, that's not difficult, okay? The problem is that tether is difficult and only carbon nanotubes were known as a possibility before graphene. But with graphene, going back to Elon, okay, the longest footbridge is the Sky Bridge, which is 721 meters. It's in the Czech Republic, okay? And people have made continuous sheets of graphene which are 1,000 meters long, 1 kilometer long, okay? But there's a problem, not single crystal. So these guys, for example, General Graphene, this is one of their long tube furnace things, and they have a roll-to-roll process, essentially. They run copper through that furnace and produce graphene on the surface, and then they can take it off the other end and put it onto a polymer. So they can produce sheets of graphene on polymers or on other sheets of graphene, okay, at a hell of a rate. They produce 60,000 to 100,000 square meters a year at the moment, and that's rising rapidly. So basically, in terms of quantity, there shouldn't be a problem. In terms of quality, there certainly is a problem. What do I mean by that? Well, the problem is that on the copper, this stuff will grow anywhere, and it won't necessarily grow aligned. It'll grow at some higgledy-piggledy angle. And that leads to regions which we call faulted regions, which are not strong, okay? So they're not that sheet would not be strong enough because it would break at that faulted region. Okay, so this kind of illustrates the problem. The graphene's growing in different places on the copper, and you can see the red bit where they join up. That would be a faulted region. But in the lab, people have now found ways around that. Two ways have been found which are commonly used. One is to say, right, well, let's suppress any small crystals from growing, and so only the largest crystals will grow. And let's taper the end of the copper so that there's a point where a crystal will start growing first. And that crystal will grow large, and the others will adjust the conditions so they don't grow, they're suppressed. And then you can make a single crystal. And in fact, in Oak Ridge, they've made a single crystal piece of graphene, which is 300 millimeters long. About a foot, okay, not too bad. But another approach is to say, well, that copper is all higgledy-piggledy itself. Those atoms are all over the place. Why don't we anneal the copper very carefully so that all the atoms are lined up in the copper so that the carbon atoms in the graphene have nice, comfortable places to sit on top, and all these different islands will grow in the same aligned manner. So that's the second approach. And some guys at Peking University have used both techniques together, and they've made a single crystal sheet which is 50 millimeters by 500 millimeters long. So you can see some progress is already being made in making this material with sufficient purity, crystal purity. Okay, look at some other applications then. Okay, if it's light and it's strong, what else can we use it for? Well, we could make a light sail out of it. We could use it as the substrate for a light sail. Light sails are being used at the moment. Craft have been launched with light sails and been maneuvered around in space. So we know we can do it. The problem is the light sails that are produced at the moment are on mylar or some other polymer material, and they're heavy. You've got to make them big, a big area, because you're relying on light hitting the surface of these things, reflecting off, and the momentum of the photons hitting the surface is pushing the thing along. And you can imagine that's quite a small effect. So basically, you need a big area to get any sort of acceleration out of this at all. And so graphene is being looked on as a possibility, because although current light sails could work in in the solar system as long as you don't get too far away from the sun, what you really want to do is you want to explore interstellar space. And so this has been predicted that if any ship is going to reach the nearest star in less than a lifetime, it's going to have to be a light sail that propels it. Many people talk about nuclear, but I think probably a light sail is more practical. Now, what people have done with graphene is they said, well, let's take some graphene, let's take a small sheet of graphene, small piece of graphene, and see if we can accelerate it. And they have done that in microgravity and in a vacuum, and shown that with a laser, you can guide it around, move it around. So the idea would be that, well, if you want to steer this thing in space, you can use lasers. You can use the solar photons to give it its basic acceleration. So you can make essentially a guidable vehicle with it, space vehicle. The sort of accelerations that are achieved are not high. A meter per second squared, that's about what you get in an office lift. But remember, as long as the light's shining on it, it's accelerating. So, you can reach quite high velocities if your craft is light enough. It mustn't be heavy. So graphene would be very useful. If you want to use powders, Orbex, a UK company, have actually used graphene powder inside an anode composite to build the shell of a space vehicle, of a launch vehicle. And they're hoping to offer very low cost orbital launch services using this kind of very light vehicle. If you're off-world, one of the things you want to do is build things. And for this slide, I had to look up the meaning of regolith. yeah, regolith is the rock powder, as it were, that you find on the surface of the moon. You've seen the boot print in the surface, in the dust, and you get that on Mars as well. And the idea is, well, could you use that to construct buildings or whatever, possibly even vehicles? And the idea is that you have to use materials that you have available rather than take them with you. So you might take a 3D printer, for example, but then if you, these people have shown that if you mix together this regolith with an elastomer and graphene, then the graphene strengthens it enough, makes it flexible enough so that you could actually make structures. And this elastomer can be obtained from biological sources like compost and urine and so on. So you're essentially being able to generate the material which you're going to use for constructing your buildings and so on, actually on the planet. Okay, now back to electronic properties. Last one really. So graphene is fast. Okay, I'm not saying Mercedes is faster than William, but you know, but essentially it's a fast. It can be used at very high frequencies because the charge carriers can be moved quickly. Okay, they have no mass. So in order to see how that might be used, we just need to think a little bit about what kind of frequency range we're interested in observing. And certainly at the moment, terahertz, or if you like, far infrared, is something that everybody wants to be looking at, because this is how the universe formed back billions of years ago. You've got essentially what you've got is you've got gas clouds that are forming planets, forming galaxies, and you want to study these, and you need to look at these in the far infrared because the distance they are, your ambient light and so on has been redshifted into the far infrared. They currently use superconductors for this in terahertz telescopes, but graphene is being looked at as a very, very useful means of detecting this radiation, because you can make graphene detectors which have about 0.1% of the power consumption of the superconducting devices, and you can make them 1,000 times smaller. So you can make the thing much denser, so you can have a denser pixel array, so you can get higher resolution in your telescopes. The picture's supposed to show how it works essentially, but it's a heterodyne process. You put a high energy beam in at the terahertz frequencies, but just slightly off the frequency you're interested in. The radiation at very low intensity is coming in at that frequency, mixes in the graphene with that, and produces a signal that is at a much lower frequency that you can actually amplify and use. Okay, but before we go on, we need to just look at the problem, the big problem, the elephant in the room, as it were. If you try to develop something like graphene and make it into a useful, turn it into something that's useful, can be used in various products, although it has all these amazing properties, there are lots of obstacles in your way. The first thing that you notice is that if you look at expectations, they rise rapidly when you see all these amazing properties. And then, okay, after a while, you get to the peak of this, everybody's explored the properties, realizes they're amazing, and you can do things with it. But then things start to go wrong because you realize you haven't got the technology, or the technology doesn't work to produce this or that. And so you drop into this sort of trough of disillusionment there. And then eventually, okay, some things work, some things get into production and start to pull other things along with them. And that's what we're hoping with space technology, is that the commercial pull from products that are hopefully going to use graphene, both for strengthening things and so on, will actually give us that pull. Because if it doesn't happen, space research itself is not going to be able to fund the equipment that's going to be required to build this stuff. If we look at predictions for mass production of graphene, well, this is what I took from some time ago, but it does illustrate the idea that it's going to rise quite rapidly. And there are lots of example areas there, okay, where, for example, battery technology, high strength composites, things like that, that are going to be used in terrestrial applications, might actually come along and pull along the space technology stuff. So that other at the top, well, part of it is space technology. Okay, and if we think about what might feed into space technology from those examples there, pretty much everything. So yeah, if things work out, then it's a good bet. To see what kind of bet we've got, we just look at some of the current applications. What is the application pull at the moment? Well, you can buy a car with a body that's made from reinforced, graphene reinforced polymer. And, you know, that's very light, very strong, very expensive. You can buy graphene skis. Now, I've skied on graphene skis. I can't tell the difference. Okay, but a friend of mine who's a very good skier says, yes, they're much more responsive than the traditional skis. You can buy graphene headphones. Okay, I believe that the high frequencies are really, really well reproduced in these headphones. Expensive again. Okay, but I believe if you're a hi-fi buff, yeah, that's not a lot for a pair of headphones. And you can get these. Okay, graphene cooled light bulb. That's basically what that does is it just uses graphene, again, the thermal properties of graphene, use it as a paste to remove heat from the LEDs. Because you've only got a thin filament there to remove that heat. So you want to do it as efficiently as possible, because if those LEDs heat up, they become less and less efficient at producing light. So, yeah, there are some examples there where we would get a good application pull. What about filtration and coatings? Well, graphene infused into plastic packaging can help improve moisture resistance. So you use thinner plastic, less plastic in the packaging. Filtration, desalination, a lot of work going on in Israel on this. Essentially, using graphene to give you cheap water desalination plants. Energy, well, graphene enhanced batteries can charge the current ones that are actually commercially available in your Samsung phones, if you have them, so on. They charge 5 times faster than the original non-graphene versions. Talking of space again, fuel cells, which are used a lot in space applications. We can use it as a means of preventing poisoning of the electrons because it's a good filter material. It filters out the damaging ion. And you might say, well, those are fine, but you're going to need, what, smallish amounts of graphene for that? Well, what about these examples where you've got concrete that's enhanced with graphene, has 25% stronger compressive strength, 25% greater compressive strength, which means you use 25% less concrete, which actually would reduce the global production of CO2 by 2%, because concrete making produces 8% of the world's CO2. It would be third on the list of countries. If it were a country, it'd be third on the list behind America, China and America. You can also add it to bitumen and cover your roads, okay? And it looks like there's a trial going on here in northbound A1 between Newton on the Moor and West Corlidge. And that the idea is one side of the road is done with the graphene enhanced material, the other side with ordinary bitumen. And the idea is to see how it responds. And from lab tests, they reckon it gives 2.5 times better wear capability than conventional materials. So again, for these, if these work okay, and it looks like they do, because this convention center was supposed to be a trial, one wall was supposed to be built with this concrete. It was so successful, they built the whole center with it. So yes, I think we can say we may be onto a winner, but we must always be a bit careful, because graphene isn't the only miracle material that's been produced in the past. Radium was supposed to be a miracle material that solved all our problems, health and so on. You could get lots of products with radium in, butter, water, makeup, everything, okay? But unfortunately, it gives you cancer. So, yeah, there may be stumbling blocks along the way. I'm not suggesting graphene gives you cancer, okay? There is a lot of work going on to see if it does, because of course, if you're working in a graphene producing powder plant, you don't want to be breathing in flakes of graphene to find that it actually is carcinogenic. So there's a lot of work going on in that area. At the moment, there's no evidence that it actually is harmful. So, okay, so graphene's material with tremendous commercial potential. That its application space technology is fairly clear. It's already having some impact in current projects in space, particularly with regard to heat removal, so on. There's a long way to go in developing new production technologies that could open up new applications which are graphene driven, like the space elevator. And new developments will only occur if there's sufficient commercial pull from, if you like, terrestrial applications, in order to allow for the investment in the huge plants that are going to be required to produce this stuff in quantities that are sufficient for the sort of impact we would like to see in space. Okay, just a quick shout out to all these guys, my ex-colleagues at Manchester. Okay, they're all still working there, and I'm blissfully retired. Okay, and thank you for listening, and I'm happy to answer any questions.